Next, we move on to preparing data for machine learning. So we have like the feature columns is equal to like all these features over here. So features columns is equal to length all the way from airport hourly flights. Basically, this contain all the features that we created, like such as like the original numerical features, the synchronical time features, the encoded like categorical features over here, and then like the engineered features over here. Then we will move on to x is equal to df.clean, feature name, and y is assigned to df.clean and delay. Then we print out the feature matrix x shape, then the feature target vector shape by using y.shape. And then we move on to for I featuring enumerate feature columns, comma 1, which prints out from I to 2D dot features over here. Basically what this block of code does is it creates a pair of like numbers and feature names, and starting from one, and then it basically prints like a numbered list of all the features being used. And then we move on to basically finding the missing variables in the features by using x null is equal to the sum. And here's the output for this. So the feature matrix shape is like 539,000 rows with 15 columns. Target vector shape is equal to 539,000 rows. Here's all the features being used. So we have length all the way down to like from airport hourly flight, and missing values in the features. This is 0, which is good. Next, we move on to from sklearn.model selection import train test split. So x train, x test, y train, y test is equal to train test split with these parameters over here. Basically, what this block of code does is splits the data into like a training and testing sets, and like 80% of this goes to training and 20% goes to testing. Next, we move on to like printing out the training set size over here, the testing set size, the training set delay rate, and the testing set delay rate over here. Then we move on to scalar is equal to standard scalar, x train scaled is equal to scalar dot fit transform x train, x test scale is equal to scalar dot transform x test. Basically, this block of code basically scales all the features, and then we move on to basically printing out the features that are scaled using a standard scalar feature means after scaling, and then feature standard scaling after scaling, and then so here's the output. So training set is equal to 431,000. Training set size is equal to 107,000. Then we have the training set delay rate, which is like 45.5%. The testing set delay rate, which is 45.54%. Then we have the features scaled using standard scalar. So here's the features after scaling. That should be around 0. So here's all the feature means over here. So they're like close to 0, which is good. And then we have featured standards from after scaling. They should be around like 1. So all these are basically 1, so which is good. And then we move on to train prediction models over here. So we begin this by basically using from sklearn and ensemble import random forest classifier, gradient boost classifier, from importing logistic regression from sklearn.linear model, importing accuracy score confusion matrix from sklearn skm.metrics, importing precision score, recall score, and F1 score from sklearn.metrics. So models is equal to the random forest with its parameters, or gradient boosting with these parameters, and the logistic regression with its parameters. Basically, this initializes the model. Then we move on to model results is equal to empty brackets, and training models is equal to empty brackets. Basically, it trains the models and then it stores the results over here. And then we do for name model and model items, print out like the training model's name. Then if a name is equal to logistic regression, and all the way till y predict prob model dot predict prob x test brackets till 1. Basically, what this block of code does is it basically uses scale data for logistic regression and original data for like the tree-based models, such as random forest classifier, and then like model fit. Basically, what this function does, it basically learns a pattern from the training data, and a model predict basically makes predictions on the delay and no delay on the test data. So yeah. Then we move on to accuracy is equal to accuracy score y test y predict all the way to f1 score y test and y predict. Basically, this calculates the metrics for like for accuracy, precision, recall, and f1 score for each of the models. So then we move on. Then we move on to model results equal to name with accuracy, precision, recall, F1 score, prediction, and probability. Train model name is equal to model. Basically, this stores all the metrics and predictions for later comparison, and like basically saves like the trained models for like future use. And then we move on to like displaying the performance for each of the models based on their accuracy, precision, and recall and F1 score. So here we have like the training models. Here's we have the training model random forest, the training model for the gradient boosting, and the training logistic regression over here. And then we move on to evaluating model performance. So results is equal to df.pd.data frame model results transform. Basically it creates a data frame and transposes it. Results is equal to df equal to results df accuracy, precision, recall, and F1 score. And then we have comparing the results, rounding up like the decimals to zero. Then we compare the results by using results df. So we have the model performance comparison for the accuracy, precision, recall, and F1 score for a random forest, gradient boosting, on logistic regression. From this, we can tell that gradient boosting is better at like accuracy and precision in comparison to like the other two models. However, random forest is better at recall, and logistic regression is better at like the F1 score. So yeah. Then we move on to plotting like the confusion matrix for each of like the models by using this block of code over here. So here we have the confusion matrix for the random forest, the gradient boosting, and the logistical regression model. So rho is equal to 0. This is like no delay, and then 1 is equal to delay. Columns equal to 0 is equal to like no delay, and 1 is delay. So for the random forest, it correctly predicted that there is no delay for like 40,668. However, it wrongly predicted for 9,756 as missing delayed. Then also it created false alarms by 21,411. However, it correctly predicted the delays by 26,642. Basically, it's good at catching like delays, but it creates like many false alarms over here. Then we move on to gradient boost and confusion matrix. So it correctly predicted that there won't be any delay for 47,707. However, it wrongly like mislabeled delays as 12,117, and it created false alarms for like 24,216, and then it correctly caught the delays by 23,837. Basically, it's the best performance out of like the three models in here. It has fewer alarms, but it still catches like the most delays. Then we move on to logistic regression. So it basically correctly predicted no delay for 46,862. It basically wrongly predicted that there would be delayed for 12,962. If created false alarms for like for 24,016, and it correctly predicted the delayed ones by 24,037. Basically, it has an overall balanced performance similar to like the gradient confusion matrix over here. Overall, the gradient boosting model is like the best one, as it basically it's like the balance of catching like real delays while minimizing like false alarms. So yeah. That was the entire project. Thank you for listening and watching.